Let's do a couple of questions, because we'll have an intro to QuarkNet shortly afterwards. So I will ask the questions from Friday, and I'll open it up to anybody to chime in. Why do bosons not have antiparticles? I feel like these are knock-knock jokes. Anybody want to chime in? Why do bosons not have antiparticles? So my response is that some bosons do have antiparticles. Our favorite bosons do not. The photon is a boson. It does not have an antiparticle. The Higgs boson, the thing that we have seen that weighs 125 protons, does not have an antiparticle. But there are plenty of bosons, like the W boson, which may have shown up in the QuarkNet exercise, is charged plus. That's why it's called the W plus or W minus. B mesons, which showed up in one of the talks earlier today, are also bosons. You can have charged B mesons. So whether or not a particle is matter-like, fermionic, or force-like, bosonic, it does not affect whether or not you have an antiparticle. So something you should think about when you go home, do neutrons have antiparticles? So neutron, anti-neutron oscillations are actually a fantastically and surprisingly important probe for new physics. What do you mean by exchange particle? Are these for me to answer? Or Thank you.
Yeah, sure. Just to not to keep Flip off the spot. So oftentimes, and it's too bad because I saw on Grant's outline he was going to do EFTs, and he didn't quite get there. But sometimes when you're looking at an interaction, you know, what was it? The high school students come into college and then they go out into the universe and you don't know what happens in between. Sometimes you model that as just like say you have two particles coming in and two particles coming out. You model that as a 4-particle interaction. But maybe you don't know that that's all that's going on. And sometimes you know for sure it's not. You know, that interaction might not have the right dimension to be a fundamental interaction, right? Could be dimension 6 operator, if you like, for the physicist judging me in the back. And so sometimes when you go to higher energies or when you examine that more carefully, you realize that in fact if you were to look carefully, that's not just 1 point interaction, but in fact there's a particle going in between. And it's actually 2 points with a little line in between. And often we'll call that the exchange particle. That's one way it might show up. Of course, it can show up in other scenarios that maybe are more familiar to experimentalists, but for me, that's what I think when I think of a mediator or an exchange particle. I think of something that's explaining an operator. Really, there's a particle sort of hiding inside. It's just at a mass scale where we can't yet resolve it. But as you go to higher energies, higher masses, that corresponds to smaller distances if you let h bar equal 1. And so you start to resolve this.
What qualifies something as a boson? So yes, the spin. So I will kick this off at my very low level. Bosonic particles have integer spin, spin 0, spin 1. So that tells you something about their angular momentum. Bosonic particles are also the particles that don't obey Fermi exclusion, which means you can stack them on top of each other, like lasers. So bosonic particles are typically what we would consider force particles, colloquially. So if you ever want to annoy a particle physicist at a bar and start a fight, you would ask whether the Higgs boson is a force particle, and they will get to this big argument about what a force particle is. And for me, I'll use a colloquial definition of something which behaves like a boson, something which does not have Pauli exclusion.
Is there a local particle physicist bar?
That is a fantastic question. Is there a local particle physicist bar? And where did we go 2 weeks ago? Captain Fatty's. So there are a couple of participants in the program who were formerly postdocs here, and they organized a social event at Captain Fatty's brewery. I'm looking at you, Lars. I'm sure Lars knows, but he's keeping that to himself.
I see enough particle physicists here.
True. Let me answer one last one. I'll pass it on to QuarkNet afterwards. Do you guys have slides? Or?
Yes.
Okay, if you want to come over and start getting set up. So the last question is, what kind of particle is a Higgs boson? And I want to end with this one because I could say it's a boson. I could say it's a particular part of the standard model. It has these particular charges. It does this thing about giving mass. I will tell you my very opinionated take on the Higgs boson. What kind of particle is the Higgs boson? It is a very cruel particle. And this generation of particle phenomenologists, some of whom have given talks here, we all got our PhDs around 2013. 2013 was a fantastic year for particle physics, where the Nobel Prize for the Higgs boson was discovered. And we had all written these fantastic PhD theses about all of the other particles that the Large Hadron Collider would discover. And if you wonder, why are all these particle physicists who were such experts on models of extra dimensions and supersymmetry and composite Higgs before 2013 now working on questions of dark matter and conformal field theory? In some sense, we're refugees from the storm that was discovering the Higgs and none of its friends. So, that was probably not the question that was being asked, but that's the answer that you're getting. So, with that, I think most of the people in this room know Shane and Ken. They are staff teachers for the QuarkNet program, which we had yesterday. So for those who are not able to attend, they are here to answer the question, what is QuarkNet?
All right, thank you very much. So first of all, how many people in here have been to a QuarkNet workshop, either at their local center, at a national program? Raise your hand nice and high. So those who are not familiar can look around and see that there are a lot of people to talk to about QuarkNet. So I know that a lot of people saw these slides yesterday, and there are a lot of people who do know some things about QuarkNet, and so I'm just going to acknowledge that up front. We are a teacher professional development program. Bullseye for us is our high school physics teachers, and we're supported by the National Science Foundation, also some indirect support through DOE and other sources as well. So we have a slide here about who we are, what we do. One of the things that I talk about, and so this is an apology to those who were at the workshop yesterday, you saw these slides already, so it's going to be a repeat.
We'll try to make it new and fresh.
All right. Yeah. So one thing that got me hooked with QuarkNet way back when I started in 2002, while I was teaching, is really getting 21st century physics things into the classroom. So when I took high school physics, I had a very good physics teacher. However, my impression of physics in leaving his class was one of physics is kind of a history course, because everything has already been measured and decided, and there's, I don't know what the professors are doing these days. Are they trying to find the more exact time that train from Seattle crosses the train from Chicago, as they meet each other? Do they have really low friction ramps that we don't have at high school level? So, I really thought as a physics educator, it was really important to me that I bring into each of my units some aspect of 21st century physics. And that was for my AP Physics 2 as well. TOO, not the number 2. Even if I had a curriculum I was supposed to follow, I wanted to make sure to work in ideas that were related to the 21st century. So we are a professional development program. We have a network. I think we have a slide coming up about numbers. But we really work to get data in the hands of both teachers and students. So we have data from CERN, from the Large Hadron Collider, from ATLAS, CMS, and others that students get to work with, that teachers get to work with. We have data from neutrino experiments here in the US. This is the NOVA detector, the FAR NOVA detector in northern Minnesota. We have a network of cosmic ray detectors that students and teachers can assemble and build and collect their own data and upload it to an eLab program, an eLab site through which they're able to share data with other folks as well. And so we really focus on getting data into the hands of students and having them have authentic science experiences. I think when learning to swim, you don't just read a book about swimming. You don't just watch a slideshow on swimming. you actually have to jump in the pool and get wet, right? And I think a similar philosophy I have, at least, and a lot of us within QuarkNet with science and physics in particular.
Another thing about, if you notice all those pictures, all those ways that we can get data to teachers and students, we also have we also have a system in which teachers have access to experts on those things.
Yeah.
So one of our previous staff members, who was a QuarkNet teacher before that, had an experience where she was in her classroom, students asked a question about, and it turned out to be about particle physics, and so this is in South Bend, Indiana, so she said, well, let me call Dr. Ruchti and ask him. And she called Randy Ruchti, and the kids were like, they couldn't believe it, but that's actually happened, and that sort of access, that sort of collegial relationship with particle physicists is part of what makes QuarkNet QuarkNet.
So we are a network of over 50 centers now scattered across universities and national labs. And I think we're up to 56 now, so this map actually we need to update. We have on the order of, actually I think probably the number of teachers who are in our program is probably more like 600 plus probably at this point. And so we have, here's a few different pictures from, so at these centers we have workshops that take place and other events. This is a picture of, actually this features some of the people in the room here, Colorado State at the top here. We have several people from Colorado State here today. But this was a part of a picture from a neutrino workshop where they're throwing these flip switches, I think they're called, up in the air. And they flip from one color to another, and kind of modeling the oscillation of neutrinos from one type to another. This is also that same group, and I got to go on this trip as well, in New Mexico with one of these cosmic ray detectors. And so it was when we had the annular eclipse, whenever that was, fairly recently, I think in 2023, late 2023, and took data during that as well. We have a cosmic ray workshop. This is at the Rice Center, and actually here's John, and our Minnesota, a group from Minnesota teachers looking at CMS data with one of our original mentors, Ken Heller there. So, so what happens at our centers is a big part of what we do, and we as staff work to support both the physicist mentors, the lead teachers, and the teachers that are at those centers.
And one of the important things about that is the ability to translate that one way or another into what we do in the classroom, either through QuarkNet, created data activities, or teachers saying, oh, I can adapt that.
Yep.
I mean, if you saw the histograms from yesterday, they're on the back. We made histograms and Post-it notes. The one on the left comes from one of our QuarkNet activities for finding the size of marbles by rolling them at each other and calculating the probability of a hit. And the other one is a Z boson mass plot. So kind of a spike, but yeah.
So a lot of opportunities for teachers. We have, in addition to workshops that occur at our centers scattered around the country, we have camps. And for us, a camp is something where we bring together teachers from many different centers. And some of those are virtual camps that meet on Zoom. We have a coding camp. Coding Camp 1 meets on Zoom for a week-long experience. And we also have in-person camps that occur often at Fermilab, for instance. Data Camp and Coding Camp 2 are two examples of that, where we bring teachers from around the country together to work on, coding or data from various experiments, going on tours, etc.
Go ahead.
No.
I would say, no, go ahead. Mention CERN first.
Oh, CERN? Oh, the CERN. Yes, we also have send about 8 teachers a year, QuarkNet teachers a year to CERN for a 2-week experience to join other teachers, part of a high school teacher program or an International Teacher Weeks program at CERN in the summer as well. So that's another great opportunity that we're able to provide QuarkNet teachers through a RET. So the REU was mentioned earlier. If you don't know, there's such a thing as an RET, Research Experience for Teachers, as well. and which is a fantastic program in itself. But we are able to use some of that funds through the University of Michigan in order to send teachers to CERN each year.
So this is where you get a show of hands. How many people in or out of QuarkNet? How many of you have gone to CERN through QuarkNet? Raise your hand. Okay. How many are about to? All right. No one has come back, not one has come back yet and said, gee, that was a waste of time.
Right, right. So in addition, we have programs, our target audience is working with teachers, but we also do have experiences that are tuned towards students. They're the ultimate benefactor, hopefully, of what we're doing. And so one of those examples is international master classes, which is something that QuarkNet and our centers and teachers and students are very involved in. This happens in February, March each year, where students from, well, actually more than 13,000 students from around the world usually participate, and they become, as we say, particle physicists for a day. So they come to a university or a national lab where they get to learn a bit about the lab, the facilities at the university. So maybe they get to go on a tour, they get to hear a talk, have lunch with physicists, I mean, kind of like lunch here, and they learn how to do some sort of an analysis and then share their data with others who are doing the same sort of analysis, and have oftentimes a video conference with a physicist at CERN or at Fermilab and other folks who are doing the same work to really model that collaboration and the discussions and so on that take place around those. And so we have masterclass measurements built around CMS data, Atlas data, Minerva data, Nova data, the list goes on, ... There's a lot more. But anyway, that's another thing that we support. In addition to, we've mentioned already, these cosmic ray detectors. We have several hundred of these. One nice thing about working with those is that it's not only the data itself, but actually the hardware and the equipment to collect the data. So there's all the joys and the frustrations that go along with that as well. One thing I really love about those is just the open-ended, like there's no ceiling. Like a student can go, as far as they want to go, because there's so many different things that they can do with it.
And the neat thing I think about using cosmic ray detectors is that there's still stuff that at least we don't know, and often we ask physicists and they're not sure either, and we can say, well, let's try to find out, and can we find out? And we learn, if nothing else, more instrumentation physics, more about the limitations of the instrument, but also sometimes, oh, that's something we can really try to measure, and that's really cool. It's a lot of fun. We had a conversation yesterday like that. So.
Yeah. So our website, quarknet.org, houses a lot of our opportunities and a lot of our resources as well, including the data activities portfolio, which currently has about, I think it's 42 activities that are found on our website, and that's a number that's growing. And most of them connect to different data strands that we have, including LHC data, neutrino data, cosmic data. And we also have coding is something that's both sort of a strand onto itself, but also one that goes with those other data strands as well. So it's good to hear that more people are wanting coding experiences. That's something that we are hearing in a lot of different places as well. And so, yeah.
Yeah, so this is our people doing stuff. So what they are actually, some of the various ways that we are able to have national camps to bring QuarkNet teachers together. So data camp at Fermilab happens every summer. How many been to data camp? All right. Yep. And we don't know who's going this summer, so we'll hold off on that question. But yeah, that's a 1 week sort of intensive workshop run by teachers. But it includes visits to some of the labs and talks by physicists. So that's one of the things we do. It's very popular. It started out as the way we trained our lead teachers when we started the program, and it became something of all its own, so teachers were able to use that. We have a coding camp, and the coding camp is online. It's 1 week, starting from, what's this Python thing I hear about, to writing, making programs, figure out how to use data and analyze it in a notebook, and have your students do the same, or even. And often what happens is it's not that you just say, okay, I did this, now you do this. It's more like, I did this, and what do you want to study? And, oh, we're interested in. I know one teacher said her students were interested in tracking hurricanes, so they started downloading data from NOAA, and they did that in their class, and did some nice results. And I think that was one of the coding camp too.
That's Fellows Camp.
Oh, that's
One of our
Fellows Camp.
So, yep.
Old eyes, sorry. Yeah. So Fellows Camp. We have camps for our teachers, lead teachers, fellows, which we'll get to who they are later, but to help develop them in order to help QuarkNet, essentially.
So a few of the resources, I mentioned the data activities portfolio, and so this is just a snapshot from the opening page. I guess it was back with the old website, but it's very similar now. So you can search by, I think that says data strand, but there's curriculum topics, data strand, level of complexity, and NGSS practice for those who are NGSS standards based. And when you click on any link, you get access to teacher notes and provide background and specific directions for teachers and so on. Any student tools that are needed, whether it be worksheets or some sort of online simulation or access to data, what have you, that's all found there as well. We also have, I mentioned eLabs, so our eLabs systems, there are 2 different eLabs. One is a cosmic ray eLab, where our several hundred detectors scattered around, students and teachers can upload data to this eLab so it can be shared, analyzed by anybody who has an eLab account. We also have a CMS eLab as well, where students and teachers have access to CMS data and are able to build plots and so on with data from there as well. I also mentioned master classes. Ken, do you want to say a little bit more about it?
Yeah, sure. So we work together with the International Particle Physics Outreach Group to present master classes essentially in our time zone. So there are different centers where the video conferences take place. So CERN is one, Fermilab is another. We sort of work with Fermilab. Well, we do work with Fermilab a lot. And then there's also one at Triumph in Canada. And there are a few others, but so international. So we do a lot. We essentially do the organizing of any international master classes that connect up or have potential to connect up with Fermilab, and so that's Atlas, CMS, Nova, and Minerva, and we still love for people to be available as moderators for video conferences among physicists out there, hello, and also for places to have master classes, host students and teachers. It's a pretty exciting one-day event. Yeah, there we go.
All right, so just bringing a few more things. We're almost done here. One thing that we do connect to is the physics that we teach. So we know that not everyone has the luxury of being able to bring in a special topics unit during their year. So many of our activities are connected to standards, conservation laws, kinematics. There are all sorts of connections that can be made with the things that we're already teaching. And so that's how I always brought in 21st century physics examples, I think I mentioned earlier, to each unit to make sure to connect the topics. And not only the topics themselves, but methods and skills, ideas and opportunities. The teamwork and the community and the networking is huge. So we have not only the local centers that build a lot of community within their own group, but also as national opportunities exist and people get to know each other, We're meant to be a long-term teacher professional development program. Research shows that one and done workshops do not work. And so it's long-term is the key, I think, to the success of the program.
And by the way, I think the methods and skills bullet is very important because we want to bring the data from particle physics, but also the way particle physicists look at data and how they analyze it. And that's something we can carry to the students, to look at data the way a scientist does.
So the last slide I have up on here is contact information for 3 of us staff members who are here. So Ken and Spencer as well. Spencer, if you give a wave. And then myself. I also have the tiny URL, which is the link to our agenda from yesterday. For those who were here yesterday, I promised I would add a link. If you refresh the page, there's now should be a link down by where it says Cloud Chamber to a form to fill out where you can get a free Cloud Chamber kit. And that is sponsored by what is it again? The American Nuclear Society. So it's not a Quark Connect gift, but I brought it up yesterday, so I wanted to make sure that I pointed that out. And in that kit, you get 4 cloud chambers, and so I ordered a kit for myself as well. But you can get a sense of what our workshops are like by taking a look at the one we did yesterday, because we do these sort of workshops at centers and at AAPT, other conferences, and so on as well. So you're certainly invited to take a look at that, and we can probably go to questions, although I do have a request. There was one question on our parking lot that we didn't get to that comes up a lot, and it was, why is this important? And so I think that would be, my request is at some point that we hear some responses to that as well. Anyway, that was a little bit of a tangent, but any questions for us, I guess, before we turn it back over? Yeah.
Yep.
So how do physics teachers join in, or how do we get to be part of QuarkNet?
I would say email one of us, and we can connect you with folks who are either in your area. We do have a virtual center as well for teachers that are not geographically located near a university or national lab. So if you email us, we can certainly help connect you to opportunities.
Raise hands again. Who belongs to the QuarkNet Virtual Center? So, yep, those are people who ask about it.
Other questions? Okay.
Okay, well.
Feel free to email if you think of one later. Thank you very much.
All right, thank you.